Welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video demonstrates the installation and testing of a two-wheel direct current robotic motor car that uses the Cytron Maker Pi RP2040 robotics controller board. The objectives of this video are threefold. First, assemble a very simple two-wheel robot car using a commercial off-the-shelf kit. Second, interface the robot car with Cytron Technologies Maker Pi RP2040 robotics controller board to drive the two front wheels of the robot car with direct current DC motors. And finally, test the robot car operations using very simple linear and angular turn movements. There are three basic categories for the robot car under test. First, there is the mechanical aspect of the robot car, which can be assembled using a commercial off-the-shelf kit. Instead of purchasing the kit, one could use a 3D printer for the parts, but the fasteners such as screws and nuts should be purchased. Secondly, there is a need for some electronics hardware to operate the robot car. The Cytron RP2040 robotics controller board fulfills this need. This board has sufficient spare ports to interface with a line follower adapter. Thirdly, some software is needed to issue instructions to the movement of the robot car. CircuitPython with some starter code would serve the equivalent of a Hello World exercise to operate the robot car. The tests for the purposes of this demonstration will be limited to moving the robot car in a straight line and turning the robot car to point to a different heading. There are several vendors for the commercial off-the-shelf robot car kit. The common parts in the kit are chassis, one piece, wheels, two pieces, encoder velocimetry wheels, two pieces, DC motors, two pieces, fasteners, four pieces, two for each motor, caster third wheel hardware, battery holder, single pole, single throw switch, assorted screws and nuts for fastening. The two key pieces of hardware for this demonstration are the robotics controller board and a desktop or notebook computer to upload the programs. The board will control the robot car. The desktop or notebook will host the code that is developed for the robotics controller board. The robot car chassis has provision for additional accessories such as line follower adapter, ultrasonic sensor, accelerometer, compass, and gyroscope, but these items are beyond the scope of the current demonstration. The direct current DC motors used in this demonstration are designated as hobby motors. The specifications of the motor are listed on the slide. Each motor has two terminals for the application of direct current. While the connections of these terminals remain static, the polarity of the signals to the terminals can be changed using the program instructions to the onboard H-bridge interface. The H-bridge circuit on the Cytron RP2040 robotics controller board manages the polarity reversal to drive the motors forwards and backwards. The kit has velocimetry encoder wheels for more precise control of the motor's rotations. Unfortunately, the opto-interrupter component to track the rotations must be acquired separately. A demonstration of this feature will be conducted in a future video presentation. The DC motor can rotate clockwise or counterclockwise depending on the polarity of the direct current signals fed to its two terminals. One rotational direction will move the car forward. The opposite rotation will move the car backward. The board uses the H-bridge circuit to dynamically change the polarity of the two terminals for each motor. This circuit permits programs to control the rotational direction of the DC motors. For test purposes, the motors will run at full speed, but owing to the support of Pulse Width Modulation (PWM) for the GPIO pin connections, it is possible to run the motors at different rotational speeds. The H-bridge circuit controls the direction of rotation of the DC motors. It is generally recommended to have a separate power source for the motors. But in the current demonstration, which is very limited in scope, a common source is used for the power to the board and the motors. The H-bridge circuit has three states. First, in the stationary state, there is no current applied to the motor. Second, in the forward state, there is direct current to the motor to rotate in one direction. Third, in the backward state, the polarity of direct current is reversed to rotate the motor in the opposite direction. Pulse width modulation (PWM) permits the application of reduced levels of power to the DC motor to rotate at less than full speed. The figure on the slide is a qualitative illustration of the effective power applied to the DC motor. An important design consideration is that the frequency of the power cycle should not affect the performance of the DC motor. PWM can be used on any GPIO pin on the Maker Pi RP2040 robotics controller board. There are 4 buttons to perform tests on the DC motors. There are 2 buttons for each of the 2 DC motors. M1A turns the first motor in one direction. M1B turns the first motor in the reverse direction. M2A turns the second motor in one direction. M2B turns the second motor in the reverse direction. The corresponding GPIO pin numbers are enumerated on the slide. These pin numbers are used in the programs to conduct the rotations through code.
On.
The status LEDs display the state of the corresponding GPIO pins assigned for DC motor operations through the terminals. The LED is on, that is, LED is lit when the corresponding GPIO pin state is high. These LEDs are very useful in determining pin signal values at runtime. There are 4 LEDs for this purpose, 2 motors with 2 terminals each. The software for this demonstration relies on the CircuitPython platform environment that for the Cytron RP2040 robotics controller board includes starter code examples for DC motor operations. The same demonstration can be performed using MicroPython, C, C++, or even Arduino code libraries because program development for the RP2040 chip is supported by these platforms too. The version of CircuitPython for the robotics controller board is 7.0.0-alpha.5. While this release has the designation alpha, which means unstable, it has been proven to work with the robotics controller board. There are several library modules included in this version that preclude the need for separate installation of the basic libraries. The onboard DC motor driver controls 2 brushed DC motors. The modules for Pulse Width Modulation (PWM) and related peripheral support, including motor libraries, facilitate quick integration of DC motors. The key library for DC motors is Adafruit Underbar Motor, which is included in most builds for CircuitPython. This library permits basic control of DC motors, leveraging PWM and H-bridge features that are normally present for robotics controller boards. The two parameters needed to instantiate the entity object for a DC motor in the program code are set to specify the two GPIO pins whose signals rotate the motor, PWM underbar positive and PWM underbar negative. The two properties of the object that can be set are decay underbar mode and throttle. When GPIO pin signal specified by PWM underbar positive is high and the other pin signal, namely that specified by PWM underbar negative, is low, then the motor will rotate for forward movement. When the GPIO pin signal specified by PWM underbar negative is high and PWM underbar positive is low, the motor will rotate for backward movement. Of course, in order to have the reverse effect owing to the mounting of the motors or user expectations, the pin designations can be reversed in the program code. The value of the field decay underbar mode sets the mode for the motor to stop. If it is set to fast underbar decay, then the motor will coast to the stop position. If the value of decay underbar mode is slow underbar decay, the motor will brake to the stop position. These settings affect the operational performance owing to the version of the chip used for H-bridge circuit on the robotics controller board. The default value for decay underbar mode is fast underbar decay. The default value for throttle is none. The two basic tests for the DC motors are movements in linear and angular directions. The application of the same power level and polarity to the DC motors will move the wheels in the same direction, either forward or backward. Applying different levels of power to each DC motor will turn the wheels at different rates, resulting in turns. It would be good to record the parameters such as power level, power duration, and distance traveled to empirically calibrate the wheel movements. The DC motor test buttons provide a simple way to check the operations of the motors. The motor will run at full speed when the corresponding button is pressed. There are two buttons for each motor, one button for the forward rotation and the other button for the backward rotation. The polarity of the motor's connecting wires sets the rotation direction for a given connection. The buttons are marked as M1A and M1B for the first motor and M2A and M2B for the second motor. The linear movement is performed by applying identical signals to both motors. It is possible to provide different levels of power to the DC motors using Pulse Width Modulation (PWM) techniques enabled for the assigned GPIO pins. The duration of the applied power controls the distance traveled by the robot car. This test demonstrates a linear movement for the robot car with two DC motors. In the first section of the code, the required libraries are imported. Then the motor properties are instantiated. To allow the motor to be physically positioned, there is a nominal delay. The next step is to set the throttle for both motors at equal values and then run the motors for 1 second, stop the motors, pause for another 5 seconds so that the user can watch the backward movement, apply the backward movement settings, run it for 1 second again, and then bring the motor to a halt. Okay, stop. There are three key functions to fulfill the linear movement requirements. These functions are: stop the motors from rotating, rotate both motors equally in one direction, for example, clockwise, rotate both motors equally in the other direction, namely counterclockwise. The robotic car accomplishes a turn by using unequal power to the two motors. In the extreme case, one motor is in the stop condition while the other motor rotates. The forward turn to the right relies on the left motor. The forward turn to the left relies on the right motor. Of course, the rotation can be reversed by using reverse power polarity to the motors. A tighter turn can be accomplished by rotating both motors simultaneously but in opposite directions. These turn movements are not very precise without auxiliary control elements and/or feedback control systems that are beyond the scope of the current demonstration. For the long turn radius, power is fed to only one motor while the other motor receives no power. For the short turn radius, power is fed to both motors but with opposite polarity. For the long turn radius, power is fed to only one motor while the other motor receives no power. For the short turn radius, power is fed to both motors but with opposite polarity. There are 4 test buttons for the 2 DC motors supported by the robotics controller board. 2 buttons for each DC motor. The linear movement demonstrations are forward and backward. The angular movement demonstrations are long turn radius and short turn radius. This video tutorial was a very simple introduction to the Cytron Maker Pi RP2040 robotics controller board. Only the built-in examples were demonstrated, including but not limited to testing the DC motors for status, linear, and angular movements. This presentation was prepared with assistance on special effects from sufisma@gmail, the documentation at Raspberry Pi Foundation and Cytron Technologies provided quick start assistance. Of course, none of this would have been possible without the free open source software from Fritzing for assembly diagrams and schematics, Inkscape for artwork preparation, LibreOffice for documentation, OBS Studio for recordings, Kdenlive for nonlinear editing, and of course, Ubuntu for the platform services. The music is from the YouTube audio library. It is called Early Avril by Unicorn Heads. Also, to my family, my teachers, from school to postdoc level, colleagues and subscribers, a simple thank you is wholly inadequate for the journey through the years. Nevertheless, thank you again to everyone on this list for the encouragement, support, and understanding to help me to continue doing what I like doing, that is, to assist in a small way to make more productive use of computer technology. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You are always welcome to be critical in any which way you can. Until next time, bye for now.